Hello, it's Keith here and welcome to lesson 56 of the platform-specific series of my Z80 programming tutorials. Now, we've looked at drawing on the Amstrad CPC before, but in the past we've always worked in sort of byte data, in bitmaps, and we've always been working in single bytes at a time. I thought it'd be a bit of fun to have a go with some pixel plotting this time while leaving the underlying pixels unaffected. So we're going to just change one pixel and leave the rest the same. Now, I've come up with some routines today that I think work reasonably well. There may well be better ones, but these are the ones that I've come up with, and we're going to learn how we can use these to draw some lines and do some other pixel based routines. So let's go over to today's code and let's have a go with it. I'll just resize my window a little bit here. Okay, so let's just fire up today's example and we'll see what it does. If I do call 120 here. Well, what we've done is we've drawn a diagonal line over here, and we've also, if you look just to the right of the basic statement here, you can see that we've actually sort of mirrored the Amstrad CPC 1985 part. We've kind of drawn it, flipped it backwards, and this was all done at the pixel level. We could have done this at the byte level, but in this case we did it with pixels. And so the code that we're looking at today allows us to do this. Okay, so how does this work? Well, let's have a look at the code and let's go over it. Well, what we're going to do is we're going to define some functions that allow us to work with pixels. Now, in mode 1, which we just saw there, and this code does have support for mode 0 as well, we've got a symbol we can enable here to turn on the mode 0 support. But what we're going to do is we're going to define some functions to work with us. Now, in the past, we've used a command called getScreenPos, which gets a byte screen position, but each byte in mode 1 has 4 separate pixels. So as well as a byte position, we also need some way of firstly changing one of those 4 pixels, but also keeping the remaining 3 pixels that we don't want to change and leaving them untouched. And so this getPixelMask function is going to do this for us. What it will do is it will return 2 masks, one that we can AND to remove the pixel we want to change but leave the background unchanged, and then another one that we can OR in to set the pixel we want to change to the maximum color 3 in that byte. Now, if we didn't want color 3, we could then sort of use another layer of ANDing to mask the color we want to put in. But as I say, this is what we're going to create today, and this is what's going to help us work with pixels. So the first thing we're going to do is we're going to get the byte screen position. Now, in mode 1, there are 4 pixels per byte. So if we are passing a pixel position from 0 to 319, which we're doing in the register pair A and B, so A is the top part of the value from 0 to 320. If we only use B, we would only have a limit of 0 to 256, and C is the Y position, and we're going to rotate B right to the right twice along with the accumulator, effectively converting this from a pixel position to a byte position. And then we're going to use getScreenPos, which is the function we wrote in the past, which will return the byte memory position of a pixel. So now we've got the byte position of the pixel we want to change. Next, we need to actually get the mask for the pixel, and the way we're doing this is with a lookup table. So if we look down here, we've got a pixel lookup here. We've got 2 versions, one for mode 0 and one for mode 1. It's mode 1 we're going to look at here. So depending on the X position within the byte, we're going to need to use the mask with the ones here for the leftmost pixel to the ones here for the rightmost pixel. So you can see there's 4 versions for the 4 possible pixels within the byte. And if you look at the way we're doing it, we're just loading the address of the pixel lookup. We're masking the 2 bits of the pixel position here, effectively getting the pixel position within the byte, and we're just reading in from that offset for the byte to set the color, and we're storing that in E. We're then flipping the bits, and we're effectively storing the byte to keep the background in D. And that's what this getPixelMask function does, and we are using that. If you look at the example here, so in this example we're drawing in the far right of the screen just here with the address 0F0, with the X position 0F0 and the Y position 0 here, and we are using this command to get the pixel mask. We're then getting a color number, and this is the color we actually want to draw to the screen. This is basically almost the same code. It's just loading in from a color lookup, and if we look at that, where is it? Here it is. So these are the masks for color 0, color 1, color 2 and color 3. And this is how we can set our color easily. So what we're doing is we are then masking the returned color from this with the mask returned by getPixelMask for the pixel we want to change. This now in E contains the pixel we want to change in the color we want to set it to. We then load in the current background from HL. We mask out the pixel we want to change, keeping the pixels we want to keep, or in the pixel we have colored up here, and then we save the result back to the screen. And we're just repeating here, increasing the X and Y positions here, drawing 32 pixels here. Now you can see here we've drawn a red diagonal line over on the right hand side there. If I change this to a 3 here and a 3 here, and then if I change this to color number 2 and compile again, do call num2 errors. Well, you can see this time, well, we've actually kind of overwritten part of it, but you can see we've drawn a cyan diagonal line this time. So you can see here we can use these pixel plotting machine routines to draw simple lines, and that's what we've done just there. Now we've effectively used the same getPixelMask function in a slightly different way down here. We've used it to copy an area of the screen, and because we're copying from left to right, top to bottom, but we are actually drawing it to the screen reversed, we've actually effectively flipped it upside down and turned it backwards. Now the only tricky thing here is because each byte contains multiple pixels, we've had to come up with some way of converting the pixel position into a color, because when we read in from the screen and mask it, we need to work out what color that actually was, because it could be in the middle of the byte. And so what I've done here is I've created a routine called byte to color mask, and what this will do is if you give it a position of a pixel and a byte that you read in, it will shift things around and convert them, and what it will do is it will effectively return the corresponding color in the same format as we were getting from our other function that was using these color lookups just here. So it's effectively the equivalent return of getColorMaskNumber, but using a byte that's read from the screen rather than a fixed number. And that's how we've been able to flip our area of the screen. Now it's just an example. If you wanted to flip an area of the screen, you would probably be better off using the code I showed you before in the previous lesson about flipping sprites. But as I say, in this case, I wanted to show some examples of working with pixels on the screen. I've actually got another little demo I've been working on that uses this same code for drawing little firework effects, which we will see later on. But as I say, for today, this is what I wanted to show you. I'm not sure this is the best pixel drawing routines, but I think it's okay. But generally, if you're developing games, I would strongly recommend you try and stick within bytes and not worry about individual pixels, because pixel work is going to be slow on an 8-bit system like the Amstrad CPC. But as I say, it was something I wanted to cover. I thought it was worth having a look at, because maybe some of you are doing graphics packages, or maybe you're doing things where the speed isn't so important, like if you've got a role-playing game and you're drawing some screens and you're sort of plotting the pixels very slowly. I thought it was worth having a look at, and it's of course a legitimate topic that people will be interested in. Anyway, that's what I've got for you today. Hope you found this interesting. If you have, please like and subscribe. Please have a look around as well, because if you don't know, I've got tons of Amstrad CPC content on this channel. Of course, I'm not just doing Z80, I've got 6502 and 68000 content, so there's lots on here. So have a look around and see what takes your interest. Anyway, whatever you do, hope you enjoy playing with the Amstrad CPC and programming in general. Thanks for watching today, and goodbye.